to receive this medal. It's something I never actually expected. I've had a passion for working in geochemistry for many years, and I've enjoyed working with so many people. Many of you are in the room here today, and without my meeting you people and working with you over the years and taking advantage of some great opportunities, none of this would have happened, and a lot of exciting research has also resulted from this. So I owe this medal more to the people who I've worked with over the years, and so thank you for participating in these research programs. It's been terrific. But today I'm going to discuss something that I feel quite strongly about, geochemistry. Many of you know that. And I'd just like to review, I guess, what works in geochemistry and what sometimes works and what doesn't work. And just sort of a review of things and mostly multi-element data. Here's an outline of what I intend to cover. Focus on multi-element geochemical survey data, looking at geochemistry in data space, the elemental and geographic space, statistics and data visualization techniques, the main challenges in using geochemical data, leveling geochemical surveys, examples of multivariate approaches used to investigate geochemical survey data, and the issue of closure and stoichiometry that I will spend some time on, and then finally a summary. I've defined the process of looking at geochemistry over the last few years in terms of two spaces, the variable space and the geographic space. The variable space being that of the elements or the oxides, in which you can apply statistics and data visualization. There are numerous graphical and statistical methods that can characterize the variables. And then there's the geographic space, where you use tools such as geographic information systems or image analysis systems, where you characterize the geographical relationships. And implied in this is that there's a spatial analysis, like geostatistical analysis, to study spatial processes. The primary goals of geochemical data analysis and the framework in which I study things is to detect inter-element relationships of geochemistry to reflect mineralogy or chemical species interactions and describe or infer geochemical processes. Also, if you're working in the exploration field, you want to isolate atypical observations or groups of observations that are potentially identified with processes of interest. If you're mapping lithological variability or till, soil profile weathering, or mineral deposit signature. There are two primary approaches to looking at geochemical data, or the phases. There's the discovery phase, in which one uses exploratory methods to discover patterns or features in data. And then there's the validation phase, or the modeled approach, where methods used to classify and confirm hypotheses through objective criteria. This could be identifying rock types or mineralization. And within the exploratory approach, things like a scatterplot matrix or principal component analysis would be used to help discover processes. And in the validation phase, techniques such as regression analysis, discriminant analysis, neural networks, self-organizing maps, and a host of other methods could be used to help validate the process you're trying to define. Well, there are many challenges in assembling geochemical data, and because I'm coming again from a government survey where we may be having large regional projects where we may have geochemical surveys from several areas over several time periods, but this also applies if you're in the mineral exploration business, where you may be going into an area where you're trying to assemble a lot of work from a lot of people to help define mineral exploration targets. So you're dealing with we're all dealing with common problems. First of all, you have different sample media. You have different methods of digestion in the preparation of the samples to the lab. There are varying limits of detection on the instrumentation, and then there's the differences in the instrumentation themselves. So if you can do it, you can possibly level the data, but sometimes that's not possible. There's no point in trying to level a sea horizon soil with lake sediment geochemistry. There are limits to what one can do. Not to say that those problems can't be explored further. Then there's the issue of censoring, where samples, the reported values are less than or greater than a detection limit. This was a problem many years ago, where people commonly took 1/2, 1/3, or some arbitrary value for replacement so that one could generate statistical moments. But now there are many good statistical methods available that help adjust and compensate for values that are reported at less or greater than detection limit. So this is one area where I think many problems have been solved. Not to say that you can't find yourself in a difficult situation if you're trying to integrate many different data sets where you have several different detection limits for the same element. So there are issues there. Then, as Juan Hope pointed out earlier today, there's the issue of missing values or structural zeros. And when is something missing that you can perhaps find a replacement for, and when is it actually a structural zero where, in fact, there's something that's not reported at all? And certainly we've found when we're dealing with mineralogy, quantitative mineralogy, it's quite common that a certain phase will not be present. So that is a structural zero. Now, if you choose to put an arbitrary replacement value, then you may be biasing your interpretation. So there are issues and things like that. And then the constant sum problem, the closure problem, and of course the obvious solution that most of us are aware of now and has been the focus of a lot of research over many years is the application of ratios and log ratios. And then something that I'm not going to address here, but I put it in the list because I believe it's important, and that is having an adequate spatial sample design. And ensuring that whatever you decide, you sample spatially, you can interpolate or you will have a spatial structure to it. If there's no spatial structure, then it may not be meaningful. Well, if you study statistics in school, or you read any books on statistics, this is what you think the ideal covariation of two elements would be. So this is gold versus arsenic. But this is in fact what we see. So we have all kinds of problems with low precision. We get quantization for instrumentation with low precision. We get censoring, we get truncation, and certainly this is far from normal. And this is typically what we deal with. Nonetheless, we still apply statistical methods and we still get reasonable results. Just to reiterate the compositional data problem and the use of log ratios, and for those who were present for Juan Ho's presentation earlier, he defined the three log ratios, the ALR, the CLR, and the ILR. I'm going to actually show examples of using all three of those in this presentation. The next thing I want to cover is leveling of geochemical survey data, and this is a common problem for exploration programs and for government surveys. I'm going to show an example of a series of 5 lake sediment surveys taken from the Batchewana area here in central Ontario. This is Canada. So here we have 5 surveys defined by the 5 colors of the dots. And there's a total of 3,000 sites. There were more than 35 elements analyzed in this survey. And if we look at some specific elements, in this case we look at zinc, we can see here in the northeast, this sheet shows an above average, or certainly higher than whatever, the higher values of zinc than we see in the surrounding area. So we have a leveling problem here, and we can express that. Okay, sorry, I thought I had a box and whisker plot, but I don't. Anyway, we can certainly see here that there's higher than elevated zinc values relative to what we see here. Well, we could level those, or we could correct for these zinc values if we consider these other areas in here to represent the true zinc distribution. Now that's an assumption that might be difficult to test, and that's an issue I'll raise later. But Bob Garrett defined a parametric leveling approach back in the mid-90s, where here I've created a synthetic sample here with chrome and 2 map sheets, and we take the quantiles of the values. So here I've defined the quantile interval of 0.05, so from 0.1 up to 0.99. If we get a line like this straight, we don't need to level. There's a good fit. We could have an offset like this, or what Bob defined as a shift, or we could have a multiplier effect where there's this change in slope, or we can have a shift and a multiplier effect. Or we can have a random association, in which case no leveling is possible. In fact, for zinc, for this Batchewana area, it's a combination of a shift and multiplier effect, and we're able to correct using that linear equation. When we do that and we plot the zinc and just looking at these two map sheets, we see a much better fit. We've also managed to preserve this area where we know there is actually zinc mineralization. So it's not a bad fit. But leveling procedure that I've demonstrated is a univariate procedure. Well, we're looking at compositions. So how do we deal with compositions? And I'm dealing with zinc that's expressed in parts per million, and you might get away with assuming that zinc is independent, because generally trace elements, you don't see the effect of closure so easily with trace elements. But the theory says that's not the right way to do things. So how do we look at this in a compositional sense? And then if we're going to level data in a compositional sense, what is the baseline? And so we run into a whole range of problems that I'm hoping will be addressed by the people interested in compositional data research over the next little while. So one of the ways that leveling is done right now is to define a conserved element or some variable by which a multivariate leveling process can be constructed. But this is arbitrary. There's not much information in the literature, and there is a need for mineral exploration industry and government agencies to come up with a consistent, well-defined process to do this. All right, I'm going to show now 3 examples of some interesting results. Here, first I'm going to show some aspects of the North American Soil Geochemical Landscape Project, which the United States and Mexico have completed their survey. Canada, unfortunately, only completed the survey in the maritime province area here, and since it's no longer a priority, but may change in the future. Quickly, to summarize, there were 3 horizons sampled. There was what's known as the public health layer from 0 to 5 centimeters, the A horizon, and the C horizon. Canada sampled the B horizon, the United States survey did not. So I'm just going to report on the public health layer, the A and the C horizon. C horizon being unweathered parent material, mineral matter, and the A horizon being oxidized, bioturbated with organic debris and extensive weathering. So here's the protocols used for the sampling. Less than 2 millimeters sieve material, less than 17% organic material, 4-acid digestion, ICP-MS for all elements except mercury and arsenic, which were done by cold vapor atomic absorption. Use of certified reference materials for quality assurance and control to ensure that all the data was properly reported and within tolerances. And we used 29 elements in this particular study. Now, here's the challenge. You have 10 political jurisdictions. We have 7 states and 3 provinces. You cannot find a harmonized geological map with all common lithologies. This was our biggest problem. And the only thing we could come up with was an Appalachian origin map which defined everything by stratigraphic groups. So after much trial and error, we decided to use this Appalachian map, and we defined a series of clastic sediments by age, mafic volcanics and intrusives, gneisses, paragneisses, orthogneisses, felsic volcanics, intrusives, and some carbonate sediments. So given this limitation in how we can use a stratigraphic framework and the range of lithologies within each of these stratigraphic groups, can we do something statistical with the data where we have this limited knowledge of the geology? By the way, this was work I did with Larry Drew, David Sutphin, and Laurel Woodward from the USGS, and Peter Frisk was involved with this from the Geological Survey of Canada. Well, why I want to show you this is because the result from the principal component analysis applied to the log-centered transform of the data showed some very interesting things. First of all, the scree plot shows that the first 3 components account for most of the variability of the data. And if we plot the first 2, or the biplot of the first 2 components, we see here a relative increase in also here we can see the green crosses as the C horizon samples, the red triangles are the A horizon, and the black circles are the public health layer samples. So we see here that there's this trend of public health layer and A horizon samples along the positive axis of the first principal component, which we see phosphorus, cadmium, mercury, sulfur, selenium, bismuth, lead, moly, tin. And this actually represents a weathering effect and the absorption of these elements into organic-rich components. And so, in fact, the organic material sequesters these elements which otherwise would weather and perhaps just disappear from the environment. We see on the left-hand side of the biplot, we see all the sea horizon, which is tightly clustered. And along the second component, we see a mafic association of nickel, chrome, cobalt, magnesium. And at the top, we see, along the positive part of the second principal component, we see barium, sodium, potassium, rubidium, niobium, representing feldspars and carbonate rocks. So we're seeing very good contrast between the basic rock types, and we're also seeing this weathering effect. And this is something that we have not seen before in a soil geochemistry profile, so we thought it was significant. Well, if we then plot these components on the regional geological map, you see here the positive scores, which I indicated down here, represent the weathered environment with the increased carbon. We see are scattered throughout here in the province of New Brunswick, and some areas down here in New York and in Massachusetts and New Hampshire. And this is, by the way, just the public health layer. So this is all this data here. If we plot the sea horizon samples only, so just these samples here, we see also quite a strong association with the lower part of the soil profile in New Brunswick and also down here in the Maritimes. What's interesting, and we're not sure why, is why Maine and Vermont, Maine and New Hampshire don't show very much. And that may be just the relative contrast, or maybe that these points sit here somewhere in the middle. So we're not sure on that. But we still see a very strong contrast between the negative, or the negative for the first principal component and the positive portion of it. If we take a look at the second component, the sea horizon only, so we're looking at this variability here in the green samples, we see here the positive scores associated with the feldspars that I indicated earlier and the carbonates in the Grenville area where there's anorthosites and high-grade metamorphic rocks, and throughout here the granitoid rocks within the New England fold belt. And we see here within New Brunswick, New Brunswick here in the Bathurst area, and the granitoid rocks in Nova Scotia, they show up quite clearly. The negative mafic association here shows up in New Brunswick, and this may reflect a lot of mafic rock that comes from just north of the border in Quebec. It also may reflect an increase of shaly material that may also contain some of these elements. So we're seeing, from this principal component biplot, we're seeing quite interesting features in the soil profile across this area. Now, if we take a look at those formations and we take and these limited number of lithologies, and we take an ILR transform of that data, and we do a linear discriminant analysis, we can see a very clear distinction here of the Devonian age classic rocks and the felsic volcanic intrusive rocks here. Here there's more overlap and mixing, but then again we're only looking at one projection of the linear discriminant functions, but this is the one that accounts for most of the variability and most likely reflects the dominant processes. If we then we do a prediction of the felsic rocks in the area. We in fact very accurately predict felsic rocks in the Bathurst camp in Nova Scotia and within the New England fold belt here and in the Grenville area. So we're able to actually, even with soil geochemistry, we can actually predict the underlying lithologies, even with some of the limitations we have in trying to create a regional map. So we feel that this was a qualified success in terms of using soil geochemistry and trying to infer process. All right, next place is the Melville Peninsula area. Working with David Corrigan at the Geological Survey of Canada. David was in that area to remap and look at the mineral potential. And here we have a fairly extensive range of lithologies throughout the area. But essentially, it's a combination of Archean granitoid rocks, Archean supercrustal rocks, including volcanics and sediments in the north. And to the south, we have Paleoproterozoic supercrustal rocks, which are composed of sediments and volcanics, and Paleoproterozoic granitoid rocks. So you'll see later that we use a very few of these because they're underrepresented in terms of the lake sediments. Now the lake sediment survey, here are all these black dots. And we see here there's a gap here where there in fact were no lakes to sample. Well, doing a principal component analysis, and also tagging each of the lake sediment sites with the underlying geology that was mapped there. If we do a principal component analysis, we get a pattern that's not necessarily easy to interpret. I mean, we see some obvious effects. We see things like cadmium, arsenic, selenium, sulfur, antimony. That possibly represents shales, clastic rocks. We see here barium, europium, sodium. That likely represents felsic rocks, felsic intrusives, felsic volcanics. And we're not sure what this pattern here is represented along the positive part of the first principal component. So in some cases we find when you have many different lithologies, it's not always easy to see an obvious process from a principal component biplot. We also see here in the scree plot, I mean, we get fairly steep scree plot, meaning that the variability is strong within the first few components, so there's something meaningful there, but not readily interpretable. If we plot the first principal component over the area, we see that it plots along this north-south trending area. And in fact, that represents the height of land. It actually reflects the digital elevation model, so it must reflect something going on with glacial processes and the preservation of the glacial material that was deposited in the lakes. So we're seeing an effect that's not necessarily lithologically related, but process related from glacial action. For the second principal component, we see a contrast between very potassium-rich, sodium-rich rocks here in the northwest to as I indicated, shales and mafic-type rocks here associated with the Paleoproterozoic supercrustal groups. So we're seeing a fairly coarse distinction between rock types. Well, if we then did as we did with the soil geochemistry, we do a linear discriminant analysis with a limited number of lithologies here, and the selection process for choosing lithologies is, do you have enough sample sites tagged for a particular geological unit that exceeds the number of elements? You need to have sufficient degrees of freedom to do this properly. And the technique for doing this was cross-validation, so we sampled this population many times and did a classification to get a stable result. And so if we compare the classification accuracy in these rocks, we get a highly successuful 82% for the Archean granodiorites, but as low as 31% for the Paleoproterozoic supercrustal rocks. We have quite a range of accuracy in predicting rock types. Even so, when we plot the posterior probabilities from the linear discriminant analysis onto the map, we get some surprisingly useful results. So here, in fact, is the prediction of the Archean granodiorite, which I indicated was about 81% successful, and it accurately describes these granodiorites as were shown on the map with very high probability. We take a look at Archean granitoid orthogneisses. We see that it surrounds the Paleoproterozoic sequence as it should. The probabilities are not as high, so there's obviously overlap with other groups, but nonetheless, we still see, it still defines what is known to be the actual orthogneisses. So similarly for the Paleoproterozoic Penrhyn group, the lower metasediments, the posterior probabilities are quite low. They're sort of in the range of 0.2 to 0.3, but still are uniquely defined relative to the other sequences in the area. And the upper Penrhyn group metasediments actually have a much better defined compositional character and able to define with a much higher probability. And I'd just like to briefly show what Patrice de Caratat at Geosciences Australia and I are starting to work on. Patrice was responsible for organizing a very large soil geochemistry survey across the continent of Australia, where there were two horizons, a top and a bottom part of an outlet sediment in the catchment areas across Australia. And each of these sediments were then subdivided into two size fractions, less than 2 millimeter and less than 75. I'll get that in a minute. But anyway, coarse-grained and fine-grained materials. And here's a biplot. And we see a very strong signature on the first component, which represents rare earth element enrichment, and probably a detrital cumulative phase through weathering process. And here we get on the positive and negative parts of the biplot something that's a little bit more difficult to interpret, and Patrice and I are actually going to be working on that. And if we just plot the PC1 according to the different size fractions and placement in the soil horizon, we see that there's more of a difference between size fraction than there is between where you are in the soil profile. So this is something that we'll be studying over the next little while. And one of the challenges we have is there a suitable map of materials, whether it be underlying geology or weathered material or regolith or some type of soil that we can map the geochemistry to come up with a classification, if that's appropriate, if we're able to do that. That's an ongoing study right now. All right, I would like to spend the rest of my presentation talking about natural laws, as it was defined by John Aitchison a few years ago. And this is the issue of stoichiometry. Well, geochemistry, from the school that I come from, is really a proxy for mineralogy. And natural laws govern the relationships of elements in the minerals, and that's based on stoichiometry. The associations of elements are not random, but governed by atomic forces that result in ordered crystalline structures. How can we reconcile stoichiometry in a compositional framework? Well, there are other additional issues. The bulk chemistry of a rock, sediment, or soil represents a mixture of mineral compositions. So we have minerals that are controlled by stoichiometry, and then we have mixtures of minerals which are controlled either by igneous processes or weathering processes or glacial processes or sorting processes. So there's many different things that can go on. So in general, the natural laws govern the chemical compositions of rocks and minerals. So crystallography 101, we have here a simple olivine. And olivine is very simple. It's magnesium and iron in one site with silica in another site. The silica form tetrahedra, SiO4, and between these silica tetrahedra and the silica is known as the M1 site, and iron and magnesium fall into the M2 site, and they substitute in that site depending on the igneous conditions. There are also other elements that will substitute for these elements for silica, magnesium, and iron. Titanium has the same ionic charge as silica, so it can also substitute. Crystal defects can accommodate things like aluminum, other similar size cations to enter the structure. But we don't need to worry about that. We're working with a simple case of olivine here. Now, to appreciate how we look at things, I guess one of the curses of geochemistry is that when geochemical analysis was developed in laboratories about 100 years ago, they reported everything as oxides, weight % oxides. And this is the result, this is more the result of the geochemical processes or the sort of the laboratory methods that were available to determine these elements, and so they were expressed as oxide. But in fact, it's not helpful for us to look at things in terms of oxides. We really need to know things in terms of molar relationships. How many moles of iron react with how many moles of magnesium or silica to form a particular mineral? So we can, and mineralogists do this through what they call the structural formula, and where you take one element of one mole of silica and 2 moles of magnesium iron, and then according to the molecular weight, you then end up with a composition here. So this is one of the challenges, because what we really, when we're thinking about mineral processes, think about geochemical processes, we're really thinking about how silica, iron, and magnesium interact. So if we form those moles, we see there is no association of silica with iron or magnesium, nor should there be. Silica is constant in the olivine structure, whereas magnesium and iron always move. They substitute for each other. But and here we see, just from these are Hawaiian olivines that I'm using in this example, we can see here that for all these samples, the silica average here in this histogram is 1, as it should be, and for iron and magnesium, iron plus magnesium, it's 2. All right, but when we get the data reported to us in weight percent, we get this negative bias. We get this relationship of silica with iron or magnesium that we know from what we just saw in olivine structure should not exist. So this is the closure issue, really summarized uniquely. And there seems no way to escape it if we're going to work in any kind of compositional framework. We can express it as molecular proportions, but it's the same issue. If we do a principal component analysis on the molar values, or the moles that I showed from the structural formula, we actually get, we see iron on one side of the biplot, magnesium on the other side of the biplot. We see silica here in the center where it should be. Now, although this looks a bit triangular, in fact, the scale of a PC2 is quite small, so this is highly exaggerated. We see that the first component is 99% of the whole variance in the data. So we're seeing a true representation of how iron, magnesium, and silica should interact, but we don't normally see the data in that form. We see it this way. We do a CLR, whether it's on the moles or whether it's on the weight percent oxide, and we see magnesium and iron opposite, as they should be, but silica always ends up on one side or the other. Now, one of the things I haven't tested yet, and this is one thing I'm hoping to work with on compositionalist friends in the future, but do we have a complete range of olivine compositions, and to make sure that we're not biased in any way in terms of where iron and magnesium relate to each other? In other words, silica may be over this way because there's more magnesium-rich olivines than there are iron-rich olivines. Those are the things that we need to look at and examine carefully. Now there's the issue of Pierce element ratios, and I find this problem really intriguing. Pierce element ratios are based on the preservation of a constituent within a magmatic system. It is the relative change of a constituent with respect to another constituent that describes compositional variation. Pierce defined a common denominator to define the compositional variation in igneous processes. And this is based on the fundamental understanding of stoichiometry. So now, if we ratio silica, we use silica as a divisor, and we ratio magnesium and iron, we get this straight line, as we should. But what we don't know, if we go back to Pearson's original comment on ratio correlations, and when also Planho did a nice job describing what Pearson and Chase had to deal with on this issue. What we don't know is this line stoichiometrically constrained, or is it an artifact of the closure? Is it an artifact of the ratio correlations effect? And from my point of view right now, I don't know. But I do know that igneous petrologists use Pierce element ratios very effectively in their work. So, and I suspect that the reason it works effectively is because there is a preserved constituent in the work that petrologists do. You cannot apply Pierce element ratios if your composition, if one of your elements in your composition is unaffected by the igneous process. Typically in let's say an igneous melt, maybe titanium may be stable or some other element. And if you use that as a fixed point and you ratio everything against that element, then you can describe stoichiometric processes related to magmatic fractionation. These are things that have not really been adequately explored from my point of view within the compositional data world, and need to tackle this. So just to reiterate, what about spurious correlations as defined by Pearson and the conserved element notion? So the use of individual elements or subcompositions may have specific uses for describing particular processes. A complete multivariate approach enables the discovery of processes through the identification of patterns and trends that are derived from various linear models. Multivariate patterns such as those described by PCA partition elements according to a number of processes. The principal balances approach, as Vera Pawlowski actually talked about today, is a promising path for dealing with singularity issues in multivariate compositional data analysis. However, I think one of the issues we need to tackle is when we create balances in the ILR, is there a way of partitioning elements? Because we know that, let's say, for example, magnesium may occur in more than one element. And if we allocate magnesium just to one balance, then we effectively block the relationship of a potential other mineral or other stoichiometric process. So these are things we need to examine. In geochemistry, these trends are defined through a combination of stoichiometric constraints on mineral formation and mixing of minerals. Decoupling these relationships in a compositional framework is a new frontier, from my point of view, for investigation. Not all these challenges have been satisfactorily resolved, as I indicated earlier. Leveling geochemical data is still more of an art. It's not well defined. It's in literature. It's not well defined in practice. How does one level for one element but not another within a compositional framework? Stoichiometry or other natural laws are not yet clearly understood or incorporated into statistical evaluation of geochemical data. And geochemical compilations have complications due to different methods of preparation, digestion, instrumentation. Can we model integration of these disparate data sets effectively? Is it worth evaluating multi-element geochemical data if there is no valid geostatistical support? This is seldom tested outside of the ore reserves estimation world. I'd like to acknowledge a number of people here that I've worked with to prepare this, and just over the years on some key areas. The Ontario Geological Survey, who allowed me to present data in Ontario. Patrice de Caratat, working with Geosciences Australia, my colleagues David Corrigan, Peter Frisk, Larry Drew, David Sutphin, Laura Woodruff at the USGS, and the gang from Girona, as they call themselves, Vera Lampol and Raymond. I appreciate all the discussion and work that I've had with them over the years. Thank you for your attention.
Eric, and we have time for questions. He's working on it. There you go.
Okay. So first of all, I enjoyed very much your talk. Not only this one, but the other two that you have given. I think they are wonderful examples of how the compositional approach can really do something in the field of geochemistry. So thanks for the applications. One short comment on the gang. The term was not invented by ourselves, but by John Aitchison, who used to call us the gang. So that's, we think it's funny, so we have adopted the term. You have put a lot of challenges, you know, with the questions you have advanced. And I think, or at least I need a lot of time to think them over. I mean, it's not you just go ahead and get a result. Just one question. Have you thought about using in the leveling problem something like, how do you call, when you made, I don't know, what's the correlation between when you have two groups of variables? Canonical correlation. Because I think canonical correlations on balances between both groups might give you a solution to the joint leveling of a whole composition. But at least I would start from there. So just a comment.
No, that's a very good point, and that's something that I had actually not considered. You know, I guess if you're taking a canonical approach, as you're suggesting, with more than 35 elements that are not necessarily, that are non-linear, and certainly important, non-normal, I don't know how effective that would be. We'd have to see. But no one has really explored this area well. So, and those who do level do assume that each element is independent, and most of the time they get away with it, you know, for the reasons I stated. That trace elements seldom seem to have an obvious effect with the closure problem. But certainly with major element oxides or any of the major elements, this would be an issue. And maybe some experimentation with canonical correlation with, let's say, the major elements might be one way to start and just see what can happen. Yeah, that's a good point. Thank you.
Yes, Jimmy.
Congratulations. I have two comments about. First is about we talk about the value domain and value space and graphic space or geographic space, right? And actually show that how statistics can be helped from graphic visualization. But the comment is that, have you considered to include the geographical information in your multivariate statistics? For example, when you're running regression of principal component, especially for detecting that process, which is your result is less effective one, and to enhance that by, let's say, giving more weights to the pattern or the rock types you already know, to include that into your multivariate statistics. So that may help you to increase the successful rate or the classification rate for that particular rock type. You could do this in iteration way. For instance, first you classify a few rock types. You felt that the results are good, and then you just to emphasis on those rock types, you have relatively few points, but you can enhance that by increasing the weights of those samples in your multivariate analysis. I think that could be a way. The other is that I'm quite interested in your ideas about this choosing a component to normalize or to do the log ratio, the divider, and so you use the Olivines and the mineral and the silic, of course, relatively unchanged for different Olivines. But if you apply that to your soil data, because the soil is a mix of different minerals, and depending upon what the process involved, therefore it will be very hard to find one single element which is relatively stable. But that's a good idea to define a divider to do the log ratio based on the physical meaning of or the property of the element, rather than just to select mean or sum. Or that's being used in the isotope studies to do the normalization. They always find a relatively stable isotopes to do the normalization. So I think excellent idea.
Well, I think the Pearson ratio approach is valid under specific conditions, and I think when you're modeling igneous fractionation, I think it works well. But if for example, the soil data, I think it would be very difficult to choose either an element or some phase or let's say some kind of index that might be able to define, let's call it a stable denominator. So I'm not sure how far you can extend this, but that's what I've indicated is a real challenge here in compositional data analysis.
We probably could do kind of statistics in the field in a given area to see which elements give you relatively less variability or something like that.
Sure, no, that's a valid point. And going back to your first point, I've actually been working with Ute Mueller at Edith Cowan University on multivariate spatial analysis. And I didn't present any of that work today because we're not done with it yet. And one of the challenges is, and actually I had this in the slide deck and then I took it out because I wanted to make sure I fell within my allotted time. But we were dealing with the minimum maximum autocorrelation factor problem, and that we're using either raw data or log-centered data. And there's to do the inverse of that may be more problematic. And we're not sure whether we can work in the ILR domain, and if so, then how do we back transform so we can interpret the results? So that's sort of, you're hitting on sort of where some of the research is going right now. So.
Yes, let's have one more question.
Eric, congratulations on your award. You have spoken about the statistical treatment of geochemical data to predict lithologies or other geological parameters. You have also made the point that geochemistry and mineralogy are intimately connected through the composition of minerals and the stoichiometry. Would you care to peer into the future and tell us what you think about the possible or the use of the advent of data that will be available from spaceborne satellites such as ASTER and hyperspectral data that will tell us something about the mineralogy and the ability, therefore, using statistics to do airborne geochemistry?
That's a great point, Patrice. Thank you for bringing that up. In fact, for example, in Australia here, one of the things that we might be able to do in the future is with the ASTER imagery identify mineral phases, of which we can then create a mineralogical composition derived from the soil data. And from that, we then can work in a stoichiometrically defined framework and provide a more effective interpretation. I guess we'll see what we can do with the ASTER data set over the next while with the results that come out of your study. That would work in a place like Australia where you've got good spectral response. In an area like Canada or Fennoscandia where you've got lots of tree cover and so on, it's kind of a different story. So, but there are certainly applications where I think that would work well. So.
All right. Thank you for that, Eric. Let's give him another round of applause. And by that,